into a box just filled with human necks.
All right, let's open up to page 78.
How about that?
We were talking about yesterday how we can kind of shy away from looking at a graph to determine where a hole or a jump might be. And we started to look at just the equations. Like, how can we analyze the equation to help us determine that information, no picture given. I forget yesterday, because every class always ends up somewhere different. I know we were on number 3. I forget if we actually checked both values. We got through 3 and 5?
Yes. Yes. Yeah.
We said it was continuous at 3 and a jump at 5?
Yes.
Perfect. Okay, so today we're going to take a look at 2, in my opinion, a little bit more advanced type problems. Okay, we're actually going to look at how we can determine continuity or discontinuous points a little differently. We're going to amp it up a bit. So the first one is in your regular notes. Okay, it's in the box. But I would like you to jot this one down underneath it. Okay, I think we should be able to at least talk about this one or try it. I pulled this example from my AP Calc class. Yes, because they actually did a whole section on continuity just like we are. Okay, so we're going to see how well we do with this one. Okay, so I pulled it from AP Calc. Now we are going to take a look at a simpler example in the box first, just to kind of get a feel for how these problems or questions actually work, and then we'll try the one at the bottom. Okay, so in the one at the box, we're going to try to figure out the value for A and B. If you look at the equations or the piecewise function, notice how we don't just have an X in there anymore. Okay, we have that A and B in there. So what we're going to try to do is figure out what should the number for A be and what should the number for B be so that we have point discontinuities, aka a hole, at the X location of -3 and 2. Okay, what's our definition of a hole? Our visual idea of a hole? Can you describe it? If we had a graph, what would it look like? What do you think, Hadley? Open circle. Okay, so 2 separate pieces, 2 separate functions that come together, and they're going to meet, but they specifically meet at an open circle. So we're trying to get something to look like that. Now, if we analyze the equation a little bit further, like we were doing yesterday, notice how -3 and 2 are those special locations, because that's where one equation ends and the next one begins. So those numbers that they told us make sense. Okay, we definitely want to check those spots. How can we determine if we're actually going to have a hole at those locations? How do we know if there's an open circle there or not? Can we look at the way the equation's written a little bit more? Can we think about the difference in the equation, whether we have an open circle or a closed circle? What do you think, Julia? Yeah. Perfect. So if you take a look at -3, okay, as it shows up for both equations, there's no bar to include that -3. So we definitely have an open circle somewhere at -3. We want to make sure that the 2 sides meet at that open circle. Okay, we don't want them to not meet. That would create our jump. The same thing's kind of going on at 2. Notice how there's no bar there to actually have a closed circle. So again, we want to make sure the left and the right meet at that open circle. So we already know there's an open circle there. What we need to test or make sure happens is that the left and the right side meet up. So just like we did yesterday, we know, let's for instance take a look at this location of -3. The left side of -3 would be the first equation, okay, values less than -3, and the right side would be the middle equation. Okay, if we want the left and the right to meet up, okay, be the same height, we want those equations to be equal to each other. Okay, we want them to be the same. So if we actually wrote that out, we'll say the left side should equal the right side. Okay, we want them to meet up. That's our definition of a whole. The left and the right side meet. Does that make sense? Mathematically, left and the right meet up, we want them to be equal. Now, if we're trying to figure out what A and B are, it would be nice if we didn't have an X in there. What do you think we can substitute in for X? Yeah. Why? That's good. That's where we want them to meet. Okay, notice how -3 was that special location where one ends and the other one begins. So if that's our special spot, let's go ahead and plug it in to show that that's our special spot. If we plug in -3 for the first X, we'll get -6, and then +3 would be -3. If we plug in -3 for the other X, we'll get -3A, and then we still have the 3B on the end. So it's nice that we got rid of one of the variables. Now our goal is to figure out what is A, what is B, but right now we only have one equation with two variables in it. Okay, notice how that's not balanced. In order for you to figure out a variable, you need one variable with one equation. Okay, nice balanced idea. So this is great, but we still have more to do to help us figure out what A and B are. Maybe we can use a similar idea with this location of 2, because that's another location where one equation ends and the next one begins. So we want the left-hand side of 2, which would be our middle equation, to equal the right-hand side of 2, which would be our third equation. So we'll set up an algebraic equation to represent that idea. Okay, we want the left and the right side to meet, so we want the left and the right to be equal. Now there's an A and a B in there too, but I would like to get rid of the X's. Okay, one less variable for us to worry about. Maybe we can plug in 2 this time, because that's where one equation's ending and the next one's beginning. So if we plug in 2, we'll have 2A plus 3B for the left. And then 2 on the right-hand side. Let's see, if we square it, we get 4. Half of that is 2. Plus 6 would be 8, minus 1 would be 7. Okay. So again, we have one equation with two variables. Unfortunately, that's not balanced, so we can't just figure out A and B by itself based off of this. But at this point, notice how we have two equations with two variables, and that is balanced. So now utilizing both equations together somehow, we should probably be able to figure out A and B. Have we heard of the word system before? A system of equations, kind of throwback to algebra. This is what we created. Okay, two equations with two variables. So if you think all the way back then in algebra, we had different methods that you could possibly use to help you figure out what are A and B in this case. Do we happen to remember those methods by name? Yeah? Substitution is one. Yeah? Elimination. Okay, so we have two different methods depending on which one you prefer, which one's more comfortable, or maybe which one's more strategic. Okay, which one makes more sense based off the equations we have. Now, do we have a preference as to which method we use? Because if we all like substitution, there's no need for me to do elimination. Do we have a preference? Do we want to see both? Yeah. What do you mean by that? Okay, so a minus and a positive.
With the B's.
Okay, so if you look at the B's, notice how we have a positive 3B here and another positive 3B there. So if they're both 3B, maybe somehow we can get them to be one positive, one negative. Take a negative out, yep. Maybe we can get them to be one positive, one negative, and that way they'd go away. Okay, so strategically, based off of how these look, maybe elimination wouldn't be the worst idea to choose. Okay, so that one might work out. Some of us might prefer substitution just because they don't want to go anywhere near elimination. Okay, now substitution, you have to pick one of the equations to use. It doesn't matter which one. And you want to get one of the variables by itself. Again, it doesn't matter which one. But you kind of have to be strategic on which one you pick and which variable you pick. So I think elimination would work better for this one, but do some people prefer substitution? Do we still want to try that? Let's do both. Okay, and then I'll let you choose which one you prefer. All right, let's try substitution. Okay, so strategically, which equation looks better for us to get one variable all by itself? Can we be kind of, not hypnotists, but magicians, if you will, and look into the future, trying to think about what would happen? Yeah?
The first one,
Why? Uh-huh.
because everything in front of the variables and numbers
Is a 3. Okay, so notice how if you wanted to get A or B by itself in this first equation, you would eventually have to divide by a 3. And if you were to divide everything by a 3, that would work out really nicely, because everything happens to be a 3. The second equation, though, if you wanted to get A all by itself, for instance, you'd have to divide everything by 2. And 3 divided by 2, 7 divided by 2, you'd have to leave those as fractions or decimals. So it doesn't matter which one you pick, but notice how one of them might be a little bit better to choose than the other one. So I would agree that the first equation would be better to pick. Now, whether you choose A or B doesn't really matter. So it's completely up to you which one you want to do. Maybe we'll get A all by itself. So if you choose the first equation to get A all by itself, we'd have to subtract over the 3b. And then to get A all by itself, we'd have to divide everything by negative 3. So all the signs are going to switch. So now that A is all by itself, we can take that 1 plus b that A is equal to, and we can plug that in to the A in the other equation we did not use. So we'd have 2 times 1 plus b plus 3b, and then equals 7. So we're kind of merging the two equations together by using this substitution method. And by merging the two together, notice how we have one equation with one variable now. So that's balanced. We should be able to solve for that variable. We can distribute and combine some like terms. So subtract the 2 over, we'd get 5. 2b plus 3b would be 5. So it looks like b is 1. All right, so there's our substitution. Now that we know what b is, how can we figure out a? Because we wanted to figure out both. How can you use one to figure out the other? What do you think, Hadley?
You can plug into the first one that we simplified, so just do 1 plus 1.
Okay, so you can plug it in here, okay, what you simplified the first equation to be, or you could plug it into one of the two originals. It doesn't matter. Okay, you have options. So you can plug it in here, here, or here. I'd agree with Hadley that this one's probably a little simpler. So if you plug in 1 for b, 1 plus 1 would give you 2 for a value of a. All right, so there's kind of a refresher on substitution. So you need to be strategic on which equation you pick and also which variable you pick if you specifically choose that method. Okay, now I kind of ran out of room. Is it okay if I erase this to go over elimination? We have it down? Okay, so elimination works a little bit differently. Elimination has a particular setup to it. Okay, you want to stack the variables on top of each other. So for instance, if I just write down the first equation the way it looks, notice how I want numbers over numbers, equal sign over equal sign, A's over A's, B's over B's. So the second equation, the way it looks right now, doesn't fit that way. You might have to rearrange the way the terms are written. So I want the 7 to be written first, and then the equal sign, and then the 2A, and then the 3B. So you may have to change the way an equation is written in order to stack them. So at this point, like we said before, the 3's in front of the b's match each other, but in order for them to be eliminated to cancel out, we need 1 positive, 1 negative. So it doesn't matter, again, which one you pick. Okay, we just want to change the sign on one of them. So just to pick one, how about we do the first equation? So if we want to change this 3 to a negative, we have to change all the other signs as well, because what you do to one, you have to do to all. So this -3 would become positive, and same with the 3 on the end. So in order for these to cancel out, we'd have to add the negative and the positive together. So the b's are gone. That's why it's called elimination. If we add the other terms, we'll get 10 equals 5a. Notice how we have one equation with one variable, so solving for a, we'd get 2. Okay, that's the same answer we got from substitution. So again, it's not going to matter which one you pick. Now that we know what one variable is, we can plug it into either of the beginning ones to figure out the other one. And if you did that, I'd bet we get a b-value of 1. Okay, so substitution, elimination, it doesn't matter as long as you're comfortable with one, you know when to use it, how it works. Okay, you work, or you do what works for you. We doing okay? We ready for the AP one? Sure. All right, let's try the one at the bottom. So instead of A's and B's, now we have K's and M's, okay, just different variables. And though I don't really have directions to go along with this one, we're not necessarily looking for a point discontinuity anymore, because notice how at this -2 location there is a bar, so we should have a closed circle somewhere. And at the 3 location, there's also a bar, so we should have a closed circle somewhere. So if we have closed circles in both places, and we're trying to figure out when would the left and the right side meet up, we're actually trying to figure out when would this piecewise graph be continuous. Okay, left and right side meeting at a closed circle. Okay, we're trying to figure out when can we draw this without lifting up our graph. So it's going to be a very similar process. Okay, at this location of -2, we want the left and the right side to meet up. So we'll set the left and the right side equal together. Just like our previous one. Now we're trying to figure out what K and M are, so it would be nice if we could get rid of that X variable. Okay, one less thing to worry about. So that's when we'll substitute in this -2 location, because that's where one equation ends and the next one begins. Okay, at that spot, we want them to match up. So if we plug in -2 for X, we'll get 4K plus M on the left-hand side. And then -8, we'll get -7 on the right-hand side. So there's one equation we can use, but notice how it has 2 variables. So we have to figure out another equation. That way we can utilize substitution or elimination to figure out what our variables are. So if this equation has to be true for the -2 location, maybe we can find another equation that has to be true for the 3 location. So when the left side and the right side meet up there, we would want the middle equation to equal the 3rd equation. Again, we're trying to figure out K and M, so if we could get rid of X, that would be great. We can plug in 3 to get 13 equals 3K minus M. All right, so now we have 2 equations with 2 variables. You should be able to utilize substitution or elimination, whichever one you prefer, to figure out what those values are. I want you to try it. See if you can figure out K and M. Any method you want.
Six times 4, 28. 4 sevens. That's a positive. Can do it.
Yeah, if you add that over.
Yeah. Four, six. He's doing some janky stuff. Negative 73.7. Is it actually? I think so. That's the number I got. What'd you put it? 4. Okay, yeah, I'll try that one. No one wasn't positive. Yeah, this one's at 13.
Oh, wait, no.
73 might not be, but it would be working out. 24 sevens. 4 times 6 is 24. 24 sevens. Because you got 4 times 6 is 24. How you don't by 6? 4 over 1. 4 times 6. 24 over 7. I got negative 73 seconds. Yeah, negative 7. Yes. Yes. That's what happens whenever you start dealing with sevens. You think it's a good. That's not how that works.
All right, so let's see how we did. I was walking around. They look pretty good. I know they're kind of weird answers, but they're still answers nonetheless, right? So depending on which method you chose, okay, I did elimination because at first glance, I noticed how M is negative in one, but positive in the other. So I know those would very nicely cancel out. Since the M coefficients are 1, substitution really would have worked well as also, because you could just move something over. So either way, it still should have worked out nicely. So in my elimination method, the M's go away. We can add everything else. 7k would equal 6. So k would be 6 sevenths. Sound good? All right. Kind of a weird answer. It's a fraction. But if you were to plug that back into either equation, your M value as a fraction should have been negative 73 over 7. Okay? For those of you that used the calculator and got a decimal value, I think it was like negative 10.43, something like that. Okay? Either one should have been fine. But notice how they're the same exact type of question, right? Whether it's in pre-calculus or AP calculus, the only difference might be the solutions in the end. How sometimes they might be fractions versus whole numbers. Okay? So you actually were doing AP calculus content today and yesterday. You just didn't know it. How we doing? Pretty good? All right. That's the end of this section. So for the rest of the period, which is a hearty 15 minutes, I'd say, I want you to work on some homework problems, whether from this section or previous ones. What's up?
Something on board, I need an explanation.